We kind of hinted at what today was going to be at the end of last time. So last time we were talking about integration, and in particular, if you want to integrate one of these vector valued functions, it's not so bad. You just do it one entry at a time. It's a good sort of mindset to have, one entry at a time. And we talked about, well, what happens if you integrate a vector valued function, and it's a definite integral? What does it mean? And we just said, well, geometrically, if somehow we can think of this as we were integrating the derivative, what we would have is the displacement. So in other words, if I have from time A, I'm at one location, at time B, I'm at another location, and what I found is I found the vector that will go between those two. And then we said, well, suppose you don't want to find that. Suppose you want to say, look, I don't want to say how far did the point move. I want to ask how far did the point travel? Because you might imagine that somehow you have a curve where you start and stop at the same point. You say, well, did it move? Well, yeah, it moved. So you want to take that into account. So now we have the question, how can we figure out how far the point traveled? So what you should think of doing is we'd like to say, hey, let's just somehow grab the curve and straighten it out and measure it. Because we'd like to measure things. And this is our favorite type of thing to measure. Now you might say, what do you mean? Well, what describes this? Well, it's flat. It's a line. We like flat things. So when we're doing integration, there's a philosophy. And this is the philosophy we have. And we're going to go into this more later on in the course, I think the third part of the course, which is integration. So what's the philosophy for integration? It says, let's take what we're looking for and let's break it into small parts. But not just any small parts, flat small parts. Because we're great at flat things. And once we've broken our things into flat small parts, we say, okay, what's happening on each one of those parts? Because it's flat, it's easy for us to do. And now we add all those answers together, and that gives an estimate. Now it's an estimate. But we can get better estimates by breaking into smaller parts. All right? Well, how do we get even better? Well, now there's this idea of getting smaller and smaller. So whenever you hear a phrase like that, smaller and smaller, that's a limit idea. So the limit idea is sort of getting somehow this notion closer and closer, smaller and smaller. It's saying what happens if you kept going. And that's where integration comes from. All right. So if you took Calc 2 last semester, you probably will say, we did something like this last semester, where we said, hey, I have some sort of curve. Doesn't matter, 2D, 3D, 4D, whatever, it's some kind of a curve. And what I can do is I can pick out some points. So, for instance, maybe we have the following. I travel the curve. Here I'm at x equals a. Sorry, not x, time. Time equals a. Here I'm at time equals b. And as time moves along, I move along this dotted curve. Well, what I can do is I can split it up. So I can say, well, here's a point t0. Then I come along, here's a point t1. Then I move, here's t2. Here's t3. And I end up at t4. So I'm splitting time. Now, as I split time, what I'm doing is I'm creating sort of some signposts along the way, saying, well, let's just sort of pause and see where I'm at. So I can look and say, all right, I can estimate my nice round curve by a series of straight lines. And so I can estimate the distance by a series of straight lines. All right, that all seems very, very reasonable. But of course, you might say, it's not very close. I can definitely see I'm off significantly. Well, what do I do? Well, more pieces. So here, how many do we have? 1, 2, 3, 4, 5. I think this is about 9 steps. And you'll see already a vast improvement. This is, I think, 13. And now you can't even really tell the difference between the line segments that are straight, that we used to approximate, and the actual curve. And that's what happens. as we get a better approximation, the difference goes away. That's the beauty of integration. All right, so again, this is what this is saying. We're breaking our time up, and so that's what happens. I broke time up, and it splits up the curve. And now I say, okay, let's look at what happens. Well, the length, going to add up the pieces. Now, what is the piece? It's a straight line. So when I talk about the length between the points, it's the length between two consecutive times. So I have some segment here. Say this is my segment I'm interested in. Well, if I want to know the distance, which is the length, I apply distance formula. Distance as square root of change in x squared plus change in y squared plus change in z squared. And that's what this means. That's delta xi. Says how much did I change going in the ith step. And similarly for the rest. So, looking ahead, we say, well, we want to turn this into something we can work with calculus. So we say, well, let's look at delta xi over delta t, and delta y over delta t, delta zi over delta t. So what am I doing here? Well, I'm essentially introducing 1. Because if you look at all these delta t's on the inside will cancel with that delta t on the outside. But it's not just any one, it's the well-chosen one. Because something nice will happen. Now, what do I mean by delta t? Well, delta xi says how far did you change in the x direction. Delta t says how much did you change in t. So now we can say, well, hey, hold on a second. X depends on t. So if I'm looking at my change in x over my change in t, it's a change of my output over my change in my input. That's roughly a derivative. So I see that the terms look like a derivative. And now I should say, look, there's an approximation here. Because it's not that delta xi over delta t is exactly the derivative, but it's about the derivative. And I should also say this is the other approximation. And then I'm breaking up my line into points. This part right here, this is actually an equals. No approximation needed. All right, well, what happens? Well, if you think about what happens, we have two things going on. There's two places where the approximations are coming into play. Well, one says the length is about the sum of the line segments. But the intuition says, as we increase the number of line segments, we split it up nicely, we get less and less error. So in the long run, when the long run says, keep splitting up t into finer and finer parts, this becomes equality. What about here? Well, where did the approximation come from? Well, it's because delta t was not 0. It was some small but not 0 number. But in the long run, what's happening is that the delta t is getting smaller and smaller. Delta t is going to 0. So, as you keep getting larger and larger, this approximation also goes to equality. Which says that, lo and behold, the length becomes now an integral. The integral from a to b of the square root of x prime squared plus y prime squared plus z prime squared dt. All right, so to recap, how did we change from Calc 2 to Calc 3? Well, in Calc 2, you did that. In Calc 3, you did that. So, you can imagine that in Calc 4, well, we know what's coming. All right, well, okay, there is no Calc 4, but if there were, we'd know what to do. We'd know what to do. Now, this is one way to derive the formula. There's another way to do this, and it's to sort of think about, well, let's think about the curve as actual motion. And let's see what that means. All right, so we're going to now think about the curve in terms of motion. Well, here's something that's easy to believe. If I want to know how far I go, I simply integrate my speed. Very believable. So distance is the integral of speed. All right. What is speed? How do you calculate speed in terms of r? Do you remember? Now speed is kind of like velocity, but not exactly like velocity. What's the difference? Yeah, it's the use of magnitude. Looks like absolute value because of our symbols. So you can say, hey, I get that distance is the integral of the magnitude, oops, and there's a typo here, not of r prime. Okay, so distance is the integral of the magnitude of r prime. Well, what is the magnitude of r prime? It's the square root of the first entry squared plus the second entry squared plus the third entry squared. Done. All right. So this might be an easier way to remember, to say, hey, if I want distance, integrate speed. And what is speed? All right. Now, I say this every semester. I hope it starts to take after a while. Square roots are not always our friends. And for years, you have said, well, boy, wouldn't it be nice if square root were friendly? No, it is not. A lot of people would say, hey, the square root of a plus b, that should be square root of a plus square root of b, because then everything's nice. It's not true. And I'll tell you that the following is also not true. The square root of a plus b plus c is not, notice the word not, the square root of a plus the square root of b plus the square root of c. Okay, so what does that mean? Well, it means the same thing that it meant before. When you're dealing with square roots, you have to be careful. Have to be careful. Now, how do you deal with square roots? Well, work with the algebra. See if there's a way to simplify what's on the inside. Can it factor? Maybe you can pull some terms out. Maybe you can't. On a really crazy day, you might do a trig substitution, but I don't think we'll actually do any of those in our class. We just like to play with the algebra. That's enough to entertain us. But perhaps in some other class, so it wasn't nice, you might have to do that. All right, so that's what we're going to do. So when we deal with the square roots, we're not going to break the rules of algebra. We're going to use the rules of algebra and be careful. Okay, well, as far as lecture goes, we're about 90% through the material. The last part is examples. So we're going to do a bunch of examples now. Any questions before we jump into examples? I suspect there's a question over here.
Yeah, so is distance the same as arc length?
Well, I like to think of distance being the same as arc length. I mean, yes, you have to be careful to make sure you have the right interpretation. But oftentimes, if you say, what's the distance the particle traveled? See, that says I'm moving along the curve. So if you're moving along the curve, that to me indicates, okay, there's something about the length of the arc. Yes, another question.
This will always be like a scalar number?
Well, so when you're talking about distance, distance is a measurement. And so since it's a measurement, it's a number. So it'll always be a number. It won't be a vector. So that's a good clue. You know, you want to get a number. And what's another good clue about this number? What kind of number should you get?
Positive.
Yeah, positive. You might get 0 if you didn't move. You know, if you're just sort of like sitting on your couch, maybe, you know, it's a polar vortex hits. It's like, all right, I'm just going to sit on the couch today. You might get 0. But you should never get a negative. So that should be a sign for us. If we get negatives, we should be very like, All right. Any other questions? All right. Well, let us begin. So suppose a particle's position is given by x of t is a half t squared, y of t equals root 2t, and z of t is log t. You know, I feel bad because I write these notes, and I did actually take an English class at one point. So a particle's position is given by. Okay, there we go. All right, now I feel a little bit better. All right. Find the distance that the particle travels from time t equals 1 to t equals 2. Okay. Well, it's a distance problem. And very conveniently, right here to the left is the formula. So we can just apply the formula. So let's see, what will this be? This will be the integral from 0 to 1. Oh, sorry, not 0 to 1. Whoops. I need to read. Yeah. Let's try that again. The integral 1 to 2. There we go. I can read. Square root of, what's x prime?
T.
T. T. Taking derivative. Yeah. T. And then we square it. T squared. Okay, what's y prime? Root 2 t. And then, well, that way, hold on. Y is root 2t, so y prime is root 2. Squared. What's z prime? 1 over t squared. All right, so we have the integral from 1 to 2, t squared plus root 2 squared plus 1 over t squared. Okay. What can we do? I'll go ahead and square that root 2. T squared plus 2 plus 1 over t squared. Any ideas?
Multiply everything by t squared inside the square root.
Find a perfect square.
Find a perfect square. Okay. It's probably a good strategy. You should hope something factors. You really, really want factoring to occur. Now, someone said, well, what if we tried to like multiply it by t squared on the inside? You know, somehow this fraction is not nice. So one thing you can do is say, well, let's put everything over a common denominator on the inside. So if I did that, I'd have t squared squared plus 2t squared plus 1 over t squared. So again, this is all inside the square root. Get everything over a common denominator on the inside. The bottom is nice and factored. What about the top? Can that factor? Whoa, perfect square. What does it factor as?
T squared plus 1.
T squared plus 1. Downstairs, t squared, of course it's a square there. And now, aha, life is good. Square root and the squares, I get 1 to 2 of t squared plus 1 over t. Good. Are we done? No, we haven't even integrated yet. But we've done the hardest part. We've handled the square root. The square root has been handled. Well, how does one go about integrating t squared plus 1 over t?
Break it up.
Well, break it up. Break it up. So think of it as t squared over t, known as t, plus 1 over t, known as 1 over t. Integral of t? Yeah, 1/2 t squared. Integral of 1 over t? Natural log of t. Do I need a plus c? No. Why? Definite integral. Definitely don't need a plus c. All right. So we plug in our 2. 1/2 times 2 squared gives us 2 plus ln of 2, which is ln of 2. Now subtract, plug in 1/2. Plug in 1. 1/2 times 1 squared, 1/2, plus ln of 1, 0. Well, it's actually subtract ln of 1, but anyways. Plus 0 minus 0, still the same. And about the only thing you can do now is 2 minus 1/2. 4 halves minus 1/2 gives us 3 halves plus ln of 2. And there we go. All right, well that wasn't so bad. Yet. Let's do another one. All right. Very similar. Suppose you have r of t is the vector valued function 1 minus t squared minus 1, t cubed. Find the length of this curve from t equals -1 to t equals +1. All right, that seems not so bad. So what should we do? So we can take derivative. Yeah, there are some things we can do. We can think of this as x of t, y of t, z of t. Because we have the r of t notation, oftentimes it's just easier just to keep it. Let's look at r prime of t. What would r prime of t be? Negative t, comma, t, comma, whoops, sorry, not negative t. Negative what? 2t. And 2t, and what's the last entry? 3t squared. All right. So we have those values. So we apply the formula for distance. What are a and b?
1.
-1, +1. And now I'm going to have the magnitude of r prime. So -2t, 2t, 3t squared dt. Well, all right. This is the integral, -1 to 1, of the square root of, now I square each term and add it up, -2t squared plus 2t squared plus 3t squared squared dt. Okay, what should we do next?
Cancellation.
Okay, well, can we cancel anything? You have to be careful because this negative will get squared. So what do I have here? I have 4t squared and 4t squared. So they become 8t squared. And the other term? 9t to the 4th. Okay, what comes next? Yeah, certainly they have something in common. So let's take what they have in common. They have t squared in common. All right. So this becomes -1 to 1, square root of t squared, 8 plus 9t squared dt. Well, okay, pull out the t squared, so -1 to 1 of t, square root of 8 plus 9t squared. Now, how do we handle the square root, though? Wait. We could do a u sub, right? Because check this out. Almost as if they wanted something nice to happen. Suppose you let u equal 8 plus 9t squared. What would du become? 18t dt, right? Hey, there's t dt. So this would become the integral of, well, you have an 18 there, so that's going to become a 1 over 18. And then you're going to get the t dt becoming du. And square root of 8 plus 9t squared is u to the 1/2. And let's talk about the bounds. Okay, so previously I went from -1 to 1. All right, well, when I set t equal -1, what do I get for u? I get 8 plus 9 times -1 squared, which would be 17. When I plug in t equals +1, what do I get? 17. All right. The integral of 1/18, the integral from 17 to 17 of u to the 1/2 du will give me 0. Because why? Same bounds, right? Okay, so this must be a case where we didn't move. Wait a second, hold on. That's weird. Let's think about this. Where are we at time negative 1? Plug in negative 1. What do you got? We have 0, 0, negative 1. Okay, so we're down here at time negative 1. Where are we at time 1? 0, 0, 1. We're up here. So somehow we were able to manage to get from negative 1 at this point to time 1 at that point, which are not the same point, and we went distance 0. We've just found a wormhole. We've changed the properties of space and time. Or we made an error. Where was our error? Do you spot it? Did we apply the formula for distance correctly? But if we did, why did we end up with 0? Did we do algebra correctly? I mean, it shouldn't be 0. So something is wrong. I just want to try to convince you that the answer should not be 0 because these are not the same point.
Can't you integrate without the bounds and then substitute back in and it'll give you a different answer?
If you integrate without the bounds and then substitute back in, you'd still end up with 0. So there's something that happened.
This is something with improper integration.
No, nothing's improper. This is very proper. This is a type of function that you wouldn't mind taking home to meet your family.
Part of the area we find is negative.
What? What do you mean by area? There is no area.
The area under the curve, the integration.
Yeah, but we're doing distance, not area. But you're right. You're on the right track.
Because it's the area under the curve, but if it's on the y-axis, there is no area.
Well, but you're thinking of area. We're doing distance. What was our mistake? There was a mistake that happened.
Did we mess up our bounds?
No, our bounds are great. These are lovely bounds.
Like you go one way and then backwards, so like adds together is 0?
No, see, it's okay to go back and forth on a curve. The distance formula will capture the distance traveled. So even if you go back and forth on a curve, it'll still say, oh, you traveled it twice. No problem. I'm still going to tally it up. It's like a speedometer. There's a movie called Ferris Bueller's Day Off, where at the end, they try running the car in reverse in the hopes that the speedometer the odometer will get reset. No, it doesn't work. So if you travel it twice, there is a mistake. The fact that we have a negative is part of it. There's something very specific.
What about if they split it into 2 and it rolls like 1, 0, 1, and 1, negative 1?
No, you still kind of run into the same issue. Well, what do I mean by the magnitude? This part? That is the magnitude, so that's okay. We did find the magnitude.
Did you do the magnitude of negative 1 to 0 plus the magnitude of 1 to 0?
I mean, you could, but if you did everything as we've done here, you still get cancellation.
If you plug the negative 1 into the square root, then you get a 1.
Well, if you put the negative 1 to the square root because you get a square, all right, I'll narrow it down for you.
Is it because you've taken the square root of a possibly negative number?
It's right here. That's our mistake. It's absolute value of t. Square root of t squared is not t. It's the absolute value of t. Now, oftentimes we're in the setting where what we're taking is positive, but sometimes we're in the case where we might have something which is negative. So this is sort of a, watch out, we like doing stuff like this because it's so much fun. Okay, so our problem was we were integrating the wrong thing. Okay, now that we know that, we're going to cross this off and think about what the right thing to do is. Now we have a problem is that we have an absolute value we tend not to like to integrate absolute values. Is there something we can do to help us integrate this to make our life easier? And I will say that there is something about this particular function.
Is it because it's symmetrical? You can do like 0 to 1.
Okay, it's symmetrical. What kind of symmetry? There's a name attached to it. It's even symmetry. So if you just ignore the integral for a second, look at this function, whether you plug in a positive t or a negative t, you'll still get the same answer. Which means that going from -1 to 0 is the same as going from 0 to 1. So the idea here says, let's change this to twice the integral from 0 to 1. And now, because I'm only going to be between 0 and 1, I can drop my absolute value. So t square root of 8 plus 9t squared dt. Okay, so here, this is using even symmetry. All right, well, what happens, okay, since we've already spent a lot of time dwelling on this topic, I'll tell you that everything else we did was fine. So again, do the same substitution, 8 plus 9t squared. du, still 18t dt. So when we do this, we're going to get a 1/18 in front. There's still the 2 there, so that becomes a 1/9 integral 0 to 1. Oh, sorry, not 0 to 1. I forgot to update my bounds. What are my bounds? 8 to 17. Aha, no one will never know I made a mistake. 8 to 17 of u to the 1/2. And now we don't get 0, because our bounds aren't the same. All right. Okay, and then we logically keep going over here. Equals star. Here's star. Okay, integral u to the 1/2. It's going to be u to the 3/2, so there's a 2/3 that's going to come in front. Because if this becomes 3/2, I multiply by 2/3. There's already a 1/9 there. So that's 2/27. U to the 3/2 evaluated from 8 to 17, which gives us a final answer of 2/27, 17 to the 3/2 minus 8 to the 3/2. Well, I said this is a final answer. I should have asked, is there anything else we can do? No. No. So that's our answer. Good. That was nice. All right. Well, let's try another one. Now, before we go on, there is an idea which we're going to need for next week's lecture. It says the following. There's something called cumulative arc length. So cumulative arc length just says, what's the total distance you've traveled so far? And in particular, saying, I want to know, I have some starting time. So we usually call it t sub naught. It's often 0, doesn't have to be. And I say, I start at time t0, I run forward some amount of time. How far have I traveled? So this is denoted by s of t, the cumulative arc length. And so again, if we go back to our philosophy, that just is the integral of our velocity. So if we integrate our speed. Now, one thing to note, and this will be, again, not so important today, but it will be important next week, is if I want to say, how fast is s changing? So what's the derivative of s? The answer is that the derivative of s is the magnitude of velocity. Now, how do we know that? Well, one way is to say, there's this cool fact called the fundamental theorem. And the fundamental theorem tells us that you should just, when you're taking the derivative of the integral from a constant to t of some function, plug t into the function. The other way is just the intuition. So I'm asking, how is the total distance changing? That's what s is, the total distance. So if I want to know how the distance is changing, I just say, how fast am I going right now? And that's the answer. the rate at which the distance is changing or the length is changing is your current speed. Now, sometimes we're interested in curves just because we're like, I want to understand this curve. And in particular, I don't want to know how the particle moved on the curve. I just want the curve itself, just only the curve. And when we want to understand that, what we can do is we can reparameterize. So parameter is just sort of this variable. So for example, we talk about parametric functions or parametric curves. The parameter we think of as t for time. And that's how we measure things. But we can change. And we can say, well, look, we're not going to go just time. We're going to go distance. So I want to say, look, I'm going to move 10 units of distance along this curve. Where am I? Well, that's an example of what you might want to do. And there are some examples like this on the quiz, or at least one. So we're going to do an example of cumulative arc length with a particular curve. This curve is called the helix. And it looks a little bit like a helix or a spring. And it's parameterized in the following way. X is cosine, y is sine, and then z is t. And so it looks kind of like this picture, like a little bit like a stretched out spring, because it's basically a stretched out spring. Now, how could we build the intuition if we didn't have the picture? So let's think about it for a second. Suppose for a minute I was standing above this picture and I was looking straight down the z-axis. When I'm looking straight down the z-axis, what that tells me is I don't know what z is doing. So it's almost like there's no more z involved. So when I look straight down the axis, z disappears. What's left? The x and y. And x and y is cosine and sine. So you should know that cosine and sine is the way to parameterize the unit circle. So when I look straight down the z-axis, I basically see the particle spinning around, cosine and sine. Now I say, okay, what is the z doing? Well, it says you spin, but now you elevate. So that's what happens. You're spinning with an elevation coming in. So that's how you get this shape. Spinning with an elevation. All right. Well, let us do the following. Find the cumulative arc length for the helix. Cosine t, sine t, t, and we're going to start at our time being 0. You might have noticed, by the way, that we used a little bit of our Greek knowledge. This is not a t. What is it? Ah, good. We have a lot of Greek people here. Yes, tau. Well, why did we use tau? Just to say, look, let's not throw in too many t's that represent different things. You never want to mix two symbols which are the same but have different meanings. Okay. So I want to find s of t. So s of t is going to be the integral from 0 to t of the magnitude of velocity. Well, that's really the derivative here. So if this is my position, what is my velocity function? Negative sine t, comma, cosine t, comma, 1. And I put t's, but I should have put tau's. That's okay. T's and tau's do look a little bit the same. D tau. There we go. All right. Well, what does this become? Integral 0 to t, square root of negative sine tau squared plus cosine tau squared plus 1 squared d tau. All right. Well, how do we go about integrating this very complicated looking expression? Yeah. We simplify this very complicated looking expression so that we have something not so bad. Trig identities are probably useful. Is there something with sine squared tau and cosine squared tau? Yeah. 1. This is the trig identity you should never forget. You can tell your grandkids when you're sitting by the fireplace, Oh, back in my day, they said never forget sine squared tau plus cosine squared tau equals 1, and that saved my life on so many occasions. All right. 1. Well, what about 1 squared? Also 1. So it's really the square root of 2, which is a constant. I can pull out constant. Square root of 2, integral 0 to t d tau. Well, that's an easy integral. It's square root of 2 tau from 0 to t. And so if you simplify, you get square root of 2 t. In essence, what this is saying is it's more or less moving at almost like a constant pace. So if I want to know how far I've traveled, it's essentially a multiple of time. Most curves don't do this. Most curves are some stretch of the curve you're going to move very quickly, other stretches of the curve you're going to move very slowly, so it's a lot more sensitive to time. But that's okay. Sometimes we have nice curves. So we've now done the first part, which was to find s of t. There's a second part, which says I want to reparameterize the helix as a function of s. So what we have for the second part is to say, you know, we have square root of 2t is s. Let's solve for t. What would t be in terms of s? S divided by square root of 2. I can just solve for t, divided by square root of 2. So now the way we reparameterize is we're going to replace our t's with an expression that's equivalent in terms of s. In our case, it's going to become s times root 2. So we get cosine s divided by root 2, comma, sine s divided by root 2, comma, s divided by root 2. So in other words, once I have my cumulative arc length function, s in terms of something involving t, I now solve for t, and I use that and replace every occurrence of t in my parameterization to get my new parameterization in terms of s. And so if I want to know, say I want to say, where am I at after I've traveled 5 units? So in other words, I start here and I travel a distance of 5. Where would I be at? How could I figure it out now? Yeah, so if I want to know, so I travel 5, where am I? Well, plug in s equals 5. Of course, unfortunately, my 5's and my s's look identical. So you're probably thinking, you're not writing down anything different. Okay, but these are 5's now. They're no longer s's. Okay, so that's the type of question that we've actually put on exams before. So you might be able to want to do those again. All right, let's see. We have 2 problems left. Wow. I don't know. We'll see how far we get in this one. We'll go quick. All right. So, I chose poorly. Okay, so we have this curve. T squared sine ti minus t squared cosine tj plus t squared minus 17k. Now, one of the reasons I like this is just to sort of emphasize there's lots of ways to write r of t. Oftentimes we're used to saying, oh, r of t, we write it in that form where you have this angled bracket, stuff, angled bracket. But you could see it in the following format, something I, something j, something k. Both are okay. Both mean the same thing. So be ready to go back and forth. Oftentimes, what you can say is, look, if I know how to do it in one format, that's enough. Because then I just have to know the one format and how to get back and forth. Okay, so I have this curve. I want to find how far do I go between 0 and root 8. Well, how do we do it? Okay, so it would be the integral 0 to root 8 of the, well, magnitude of r prime. All right, that's just the formula. Good place to start. 0 to root 8, magnitude of, for r prime, well, what rule do we need to take the derivative here? Product rule. We're going to have to do the product rule in each entry. Really? Yes. Why? Because we can. And I screwed up already. Okay. I should never talk while I'm deriving. All right. Don't talk and derive. So t squared cosine t plus 2t sine t. That's the first entry, comma. Then I get t squared sine t minus 2t cosine t, comma 2t. All right. Now comes the fun part where we get faced with a huge square root. T squared cosine t plus 2t sine t, quantity squared plus t squared sine t minus 2t cosine t, quantity squared plus 2t squared dt. Now, there's a couple of options at this point. One is just to say, it's only one problem on the exam. I'll just take the loss. Now, if you got to this point, you probably get like half the points. You know, because a surprisingly large number of points are about setting things up. That's actually a huge chunk of Calc 3 is learning to set problems up. The computation part, that's not quite worth so much. But no, we want all the points. Got to get them all. Got to get them all. So what do? You do your beautiful algebra. You square stuff. You get t to the fourth cosine squared t plus 4t cosine, 4t squared cosine, 4t cubed cosine t sine t plus 4t squared sine squared t. I'm running out of space. So on the next line underneath it, I'll write t to the fourth sine squared t minus 4t cubed cosine t sine t plus 4t squared cosine squared t, and then I have a 4t squared on the end. Now, lo and behold, what happens? Things get nice because calculus is beautiful. So nice things should happen. We're good people. Okay, what happens here? T to the fourth cosine squared plus t to the fourth sine squared? T to the fourth. 4t squared sine squared plus 4t squared cosine squared? 4t squared. And there's another 4t squared, so we're going to double down. That's going to make us 8t squared. It becomes beautiful. Now what happens? Pull out a t squared. Square root of t squared is t. Wait, is it absolute value t or is it just t? It's absolute value or it's just t because we're positive. You always double check. Be careful because, you know, fool me once, shame on me. Fool me twice. It's not nice to fool people. All right. And etc. because time is up. All right. We'll pick up again next time.